All right, today we're looking at more series manipulation. This is for both series manipulation days, so the one right before the quiz and the one right after. The first thing we're going to look at is geometric series and how they work and how we can use them to manipulate some Taylor and Maclaurin polynomials. So this is just some practice writing some geometric series. Remember, when we write a geometric series, A is the first term, and then R is the common ratio. So in this case, 2 plus 2 times R, which is 6, plus 6 times R, which is 18. Can't do math. Plus dot, 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 dot. Similar thing here for the second one, starting with 2. Then it would be 2 times negative 3, which is negative 6. Negative 6 times negative 3, which is positive 18. And keep going from there. Well, that same idea can be applied to things where R is the x, or is x. So in this case, we have 1 plus x squared plus x cubed plus dot, 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 so on and so forth. This idea leads to what we call the geometric shortcut. It allows us to take a function that looks like the sum formula of a geometric series and write it as a geometric series. Perfect example is right here for f of x. This looks kind of like the geometric series sum, where 1 is our a and x squared is our r. So we can write a series here that is 1 plus x squared plus x to the fourth plus x to the sixth. So we're just multiplying each term by r. And then our general term would be 1 times x squared to the n power. All right, now what we'll notice about this though, unlike our other Taylor-Maclaurin series that we've made before, this isn't a perfect match. It's only a match for our radius of convergence. So we're going to instead use our geometric series test to find this radius. So remember, geometric series test said absolute value of r had to be less than 1 for it to converge. And it diverged if absolute value of r is greater than or equal to 1. So in this case, r, lowercase r, is x squared. So we have absolute value x squared is less than 1. So our interval of convergence would be -1 is less than x, which is less than 1. But here's the thing. Unlike with our other times we've checked for radius of convergence and interval of convergence, we don't have to check the endpoints, because if r is equal to 1, it diverges. So there's no need to check the endpoints for this. It's just going to be this interval here. That's it. And this applies to other problems as well. Now, let's look at this one first. This one's a little bit different. It's centered at x equals 3. So for these problems, the first thing you have to do is make sure you get your center to align, which means we're going to change it to x minus 3 here. Now, if you know anything about math, we can't just go adding or subtracting something without balancing it. So to balance, we actually added a positive 3. This is negative times a negative, so that's plus 3. So we're going to have a minus 3 here. So we have 5 over 1 minus x minus 3. Now it is in the right form. Now, this form only works if this is a positive 1. So you have to get that to a positive 1 first. So we end up with our a is 5, and our r is x minus 3. So our series would be 5 plus 5 times x minus 3. And each time we're just multiplying by a new x minus 3. So 5 times x minus 3 squared, 5 times x minus 3 cubed, dot, 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 5 times x minus 3 to the n. So now we have a geometric series. Once again, this is the geometric shortcut. So this is a Taylor-Maclaurin series. In this case, it's a Taylor series centered at 3. And it's a shortcut to get that. You could still go through the process of finding f prime of x, f double prime of x, f third derivative of x, and then plugging in c to use the whole Taylor-Maclaurin series formula to create this series. but this is a shortcut for it so that we don't have to do as much work. It just only works for these geometric series. Now, one thing I want to talk about here is the interval of convergence. Since this is a geometric series, we know that the absolute value of r has to be strictly less than 1. So that means if we're looking for the interval convergence, x minus 3 has to be less than 1. So our radius is 1. And then we end up with, what is this? So 2 is less than x is less than 4. And we don't have to check the endpoints on these geometric ones because r has to be less than. There's no equal to opportunity there, just less than. So that is our interval. Now I do want to make a small change to this problem and see how it's different. What if this was 6 instead of 4 here? So now, when we do our realigning our center, we get 3 minus, and then x minus 3. This doesn't change our work, but we still have to get 1 here first, a positive 1. To do that, we're going to divide everything by 3. So we have 5 over 3, 1 minus, and then x minus 3 over 3. So our a is 5 over 3, and our r is x minus 3 over 3. So our series would be 5 over 3 plus, and then 5 over 3 times x minus 3 over 3, plus 5 over 3 times x minus 3 squared over 3 squared, plus dot, dot, dot. And we just actually simplify those. So 3 times 3 is 9, 3 times 3 squared is 27, so on and so forth. Okay, so keep that in mind when you're working. Now, we also have this idea of being able to find the sum of a series now. With these new Taylor and Maclaurin series, it's now not only just geometric and telescoping we can find the sum of. For example, this first series looks like e to the x, kind of. It looks like the series we created for e to the x, except it has 3 plugged into x. So that means this series is equal to e to the x with 3 plugged into the x, e cubed. So that's what this sum is equal to. Same thing can apply to sine and cosine. Like for example, for this second one, this looks like sine with 2 plugged into the x. And remember the sine formula is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot, 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 dot. Well, look, that's 2 cubed, 2 to the 5th, 2, 2 to the n, 2 to the 2n plus 1. Okay? Now, that doesn't mean we just ignore geometric series. Like, for example, this last one, this is a geometric series with an r that is less than 1. So this would be 1 over 1 minus, and then negative 2/3. So that would be the sum of this one. It's just now we have more ways to find the sum. Okay? Now, we also want to talk about derivatives and integrals when talking about radiuses and intervals of convergence. So you can take a second to write all this down, but the idea here is that when we take the derivative of a power series, the radius of convergence stays the same, but the interval will change. And I don't mean the numbers in the interval will change. I mean the less thans. So it could change from less than to less than or equal to, or from less than or equal to less than. So let's look at an example. We have this series, 1 over 1 minus x. This is a geometric series. We can use geometric shortcut. F of x is 1 plus x squared plus x cubed plus dot, 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 x to the n. All right? It converges when absolute value of x is less than 1 because it's geometric. So between negative 1 and 1. Now, we want to find the derivative of this. Well, we'll just do the derivative of each term. So 0, 1 plus 2x plus 3x squared plus 4x cubed plus dot, 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 n times x to the n minus 1. All right? Now, we want to find the values of x for which the series converges. That's just the interval convergence. But this is no longer a geometric series. We can't just say absolute value of x is less than 1. But the thing is, because it is the derivative of this one, the radius is the same. We can use the same radius. Absolute value of x is less than 1. So we have negative 1 is less than x, which is less than 1. The issue is, where in the first one we did not have to check the endpoints because it was geometric. Since this one is not geometric, we have to recheck the endpoints to make sure it doesn't converge at the endpoints. So we have the sum from n equals 1 to infinity of n times negative 1 to the n minus 1. Well, this is going to diverge by alternating series test. If we get rid of the alternating part, the limit is not equal to 0, so it diverges. Let's check the other one, n equals 1 to infinity of n times 1 to the n minus 1. This one is also going to diverge by term test, because 1 to the n minus 1 is just 1, so the limit as n goes to infinity is infinity. So both of these diverge, which means we don't have to change our interval. But that's not guaranteed to be the case. You will have some where in the original interval, they both diverged. But once you take the derivative or once you take the integral, then one of them might converge. Now, we can also use this to come to conclusions about problems like like part C. We want to use this series to find, or use the series from B to find the sum of this infinite series. Now, that doesn't mean we're going to add together all the terms of the series. It means what can we gain from information about part B that will let us find a sum here? Well, first and foremost, this looks like part B with 1/3 as the x. Okay? Well, part B was the derivative. So that means this part is f prime of 1/3. Well, how does that help us? Well, we know what f of x is. F of x was 1 over 1 minus x. So if we can take the derivative of this and plug in 1/3, then we'll know what the sum is equal to. So let's take the derivative. This was 1 minus x to the negative 1. So that's going to be negative 1 over 1 minus x squared times the derivative of the inside is negative 1. So that gives us 1 over 1 minus x squared. So now if we want f prime of 1/3, it's 1 over 1 minus 1/3 squared. 1 minus 1/3 is 2/3. 2/3 squared is 4/9. So 1 over 4/9 is 9/4. So this series converges to 9/4. All right, so these are all just extra manipulation techniques and some understandings of how things can be manipulated. Let me know if you have any questions. Feel free to send me an email if you need anything. You all have a great day.